Hello everyone, welcome to today's session on sorting algorithm. Whenever we work with large amount of data, keeping it organized becomes very important. Imagine searching for a student's mark in randomly arranged list. It would take much longer than searching in a properly ordered list. Am I correct? So sorting algorithms helps us arrange data efficiently and making searching, analyzing, and processing much faster. In this lecture, we will learn 6 popular sorting techniques and understand where each one is useful. So, before we dive into each algorithm, let's quickly see what we will be covering. We will start with bubble sort, which is one of the easiest algorithms to understand. Next comes insertion sort, which works similarly to arranging playing cards, and then we will look at merge sort, quick sort, and then much more commonly used larger data sets. We also study the bucket sort and keep sort, each designed for specific situations. By the end of this session, you will know how each algorithm works and when it should be used. So here so here let's begin with bubble sort. This is probably the simplest sorting algorithm. The idea is very straightforward. We repeatedly compare two neighboring values, and what happens next is, if they were or not in the correct order, we simply exchange their position. This process keeps repeating until every value reaches its correct place. The reason it is called bubble sort is because the largest values gradually move toward the end of the list, just like the bubbles rising to the top of the water. Next, the slide is about we start from the beginning of the array. The first two numbers are compared. If the first number is bigger, we swap them. Then we move one step forward, compare the next pair. This continues until we reach the last element. At the end of the first pass, the biggest values automatically reaches the last portion. And this is about the remaining passes. After the first round, we don't have to compare the last element anymore because it is already in the correct position. So during the second round, we compare only the remaining unsorted part. Again, the next largest value moves its correct place. This process repeats until all elements are arranged. And this is about the unsorted boundary strings, in which you notice something which is interesting here. With every pass, one more element becomes permanently sorted. That is correct. Am I correct? This means the area we need to check becomes smaller and smaller. So instead of checking the whole array every time, we only focus on the unsorted portion. Next, eventually all the elements reach their proper positions. At this end of the stage, no more swapping is required. The array is now completely sorted in ascending order. Although the bubble sort is easy to understand, it is not the best choice for very larger data sets because it performs many comparisons. Then this is about the bubble sort complexity. If the data is already sorted, the bubble sort finishes quickly. So automatically the best case is order of n. But when the data is completely random or in reverse order, it takes much more time. That's why it is average, and the worst case performance is quadratic. The good thing is it requires only a small amount of extra memory. So the space complexity is order of 1. Regarding the insertion sort work is in a different way. Here it is think about the arranging cards in your hand. Whenever you receive a new card, you randomly place it. Am I correct? So instead you find the correct position and insert it there. Insertion sort follows exactly the same idea. It builds a sorted version gradually and one element at a time. Initially we assume this first value is already sorted. Now pick the next value. we compare it with the shorted portion. If necessary, we shift larger values to the right and insert the current value into the current location. This process keeps expanding the shorted section. So once again I repeat, suppose if we pick the next value, it compare with the shorted position. Next, if it is necessary only, it is going to shift the larger values to the righter position and then insert the current value to the current location. Okay, next now we repeat the same steps for the next values. Sometimes the new value is already larger than everything before it. In that cases, we don't have to move anything, we simply leave it where it is. Next, when a smaller values appears, we shift all the larger elements one position to the right, then we insert the value into the empty position that was created. This continues until every element has been inserted correctly. Next is about insertion sort performs very well when the data is already shorted. So however, if the data is completely shorted, many shifting operations required. We are going to that there may be a possibility of little additional memory compared with that of the bubble shot. Likewise, like the bubble shot, it also uses the same amount of additional memories. Next is about the merge sort. Here the most efficient sorting algorithm is called merge sort. Instead of sorting everything together, merge sort breaks the problem into smaller pieces. Each small piece is sorted independently. Finally, all the sorted pieces are combined to produce the final sorted array. This strategy is known as divide and conquer. Next is about the splitting the array. Here each half is divided again. Here we divide the original array into two halves. So this process continues until every group contains only one element. A single element is already sorted, so there is no further division is needed. Am I correct? Next is a divide and conquer strategy. After dividing, the algorithm starts solving the smaller problems. Each tiny array is sorted individually. So once they were sorted, they are merged together step by step. Eventually, all the small sorted groups combine into one completely sorted array. This was shown in this diagram. And the next one is divide and then merge concept. Here this picture clearly shows the complete process. The left side represents dividing the array repeatedly and the right side shows how these small pieces are merged back together into the sorted array. Here this is why the merge sort is most efficient and reliable. With this picture you can clearly understand the working concept of the merge sort. Next is about its sort complexity. Here the one of the biggest advantage of the merge sort is consistency. So whether the input is already sorted or completely random, its running time remains almost the same. Am I correct? The only drawback is that it needs extra memory while merging. Next sort is about bucket sort. The bucket sort works differently from the previous algorithms. Instead of comparing every element, it further groups similar values into different buckets, and after sorting each bucket separately, all the buckets are joined together. This approach works especially well for the uniformly distributed data. So uniformly distributed data, it works well. Next one is the scatter and gather approach. Here the entire algorithm can be remembered using three simple steps. First step, distribute the elements into the buckets. Second, sort the entrance of each bucket, and then finally combine all the buckets in sequence to obtain the sorted output. So you have to first distribute the elements and then sort the elements, and finally you have to combine those in the sorted format in all buckets. Next one is about creating buckets. Here it is creating buckets. That is in this example we first create the empty buckets. Then we examine every value in the array. Depending on its range, each value is placed into the appropriate bucket. Next one is filling buckets. Here you have to let's see this. Here values that fall in the same interval go to the same bucket, then grouping reduces the amount of work needed together. So here the similar values are grouped together, that was explained in this slide. So the values values of same interval are put into the same bucket, that is mentioned here. Next one is you have to sorting and finally gather the individual buckets. So here each bucket is sorted independently. Since each bucket contains only few elements, sorting becomes very fast. Different sorting algorithms can be used inside each bucket. Next here finally we are going to collect the entire bucket values. So with the final collection, once every bucket is sorted, we simply read them one after another, then the combined result becomes the final sorted array. A bucket sort is extremely efficient when the input values are evenly distributed. Before that we saw about the merge sort, you have to mention that is uniform distribution. Here also there is a uniform distribution is needed here. Next one is about the quick sort, so which is the fastest sorting algorithm. The main idea is selecting one special element called the pivot, and the pivot divides the array into two groups. Smaller values go to the one side and the larger value go to the other side. The same process is repeated recursively. So this is mentioned in this slide, and the next slide is about the last element is selected as the first suppose if the last element is selected as the pivot element, then different versions of the quick sort may choose different pivot positions. The choice of the pivot completely affects the algorithm's performance. So starting from the left side, we compare every element with the pivot. If an element is smaller, it stays on the left. Otherwise, it waits until a suitable swap occurs. That was explained in this slide. And this slide is about rearranging the elements. So when we find a smaller value after a larger one, we exchanging their position. This gradually moves smaller values towards the left side of the pivot. Next is about tracking the elements, which is continuing the process by the same comparison and swapping continuous until every element has to be checked. At this point, all smaller values are on one side and the largest values on the other side. So this was mentioned in this slide. Here the last element compared with that of the other elements which are in the pivot is stored in the last position. Next is about recursive sorting, which is because it is this process repeats until the whole array is sorted. So the remaining sub-arrays are processed in exactly in the same way. Eventually every pod becomes sorted and the recursive process continues until one single element arrays remains. So here you have to repeat the process until one single element array remains. This is shown in this diagrams. Okay, and this about the sort complexity, the best is order of n log n and the worst is order of n square and the average is order of n log n. So here the average and the best case is the same value, whereas the space complexity needed for the quick sort is order of log n. Next this is about the entire sorting algorithms. There are several algorithms, but what we have covered today is about the sorting algorithm is in the syllabus only. So based upon the syllabus we are presenting the sorting algorithm. This brings to the end of the today's session. We learned 6 important sorting algorithms and understood how each one organizes data differently. Remember, no single algorithm is best for every situation. The choice depends on the factors such as data size, memory availability, input characteristics, etc. So thank you for your attention, and so see you in the next lecture. Thank you.